Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Today we're continuing our two-part series. Here it is. Using FESTO-Motion with Horner OCS. In part one, we did something we thought was fun, and we integrated these two products, the Horner OCS and FESTO-Motion, and we did so using register-based advanced ladder. Now, register-based advanced ladder is a little bit old school, but we've got a lot of users still using that programming style, so we thought, let's give these folks a head start with a nice detailed example program using their preferred style so they can get FESTO-Motion and the Horner OCS up and running in their next application. But today for part two, we're getting a little more advanced. Today we're using variable-based advanced ladder, which means we have the ability to use user-defined function blocks, arrays, and other advanced tools. And we've created a couple of user-defined function blocks specifically for use with FESTO-Motion so that you can have a really nice system integrated between the Horner OCS all-in-one controller and FESTO-Motion. Now, it's a pretty inclusive topic today, so let's get right to it and break down today's topic. Okay, we're going to start out today with a quick review of the FESTO-Motion control system in Horner OCS. We won't spend too much time on that because we covered it pretty thoroughly last week. And then our main topic, user variable-based logic and user-defined function blocks for FESTO-Motion control with the Horner OCS. That's where we're going to spend a bulk of our time today. Okay, but let's get going on that quick review. All right, so we're going to be dealing with the Festo CMMT-ST servo drive for this demo, just like last week. A really nice product. Head to the Festo website to check out all the information on their great motion control products, but we're utilizing the CMMT-ST. Our demo system today is going to be based on Canvas. Last week, it was based on an XL4. This week, we're using our most advanced Horner controller, the Canvas series, and specifically the Canvas 7. We'll be using that with the CMMT-ST drive, and one of the great things about that drive, it has the versatility to support a lot of different types of motors. We're using the version that supports stepper motors, so that's what we've got today on our bench. Okay, now there's all kinds of resources available that you'll need for your application. Lots of user documentation available on the Festo website. You're going to need the Festo Automation Suite setup software. Now, I covered that briefly last week, so you can go back to last week's video if you want to check that out, but you will need that for your application. Of course, you'll also need Horner's Cscape program, and since we're utilizing Canvas, we're going to require Cscape 10 for today's demonstration. If you're not using Canvas and you'd like to take advantage of these user-defined function blocks, that's no problem, but you will need to use Cscape 10 because we have developed these UDFBs using Cscape 10, and you can't go backwards, if you will. Okay, and you can download those files from our website with the demo files that are tied to this particular video. Okay, so how does the actual motion control work between the Horner OCS and the Festo drive? Well, it really works the same way as it would with any PLC. The Horner OCS is acting as the PLC here. You've got 12 words of data going each direction at high speed over an Ethernet connection between the drive and the Horner OCS. You've got 12 words of status coming from the drive to the OCS, and you've got 12 words of control going from the OCS to the drive. Okay, now taking a little closer look at these status words and control words and how those are designed by the Festo folks. One thing to note is Festo has several different application notes which go through this in detail, and I would highly recommend you check out their great application information. Basically, the way they've designed this interface is that it's the same in terms of the word exchange is the same for both Modbus TCP as well as Ethernet IP. So really the documentation applies to both. So again, lots of great application notes available on the Festo website. But the bottom line is you've got these 12 status words and 12 control words. Now it just so happens that the first few of each of these are bitmapped integers. So the first 5 status words coming back from the drive are actually bitmapped integers. So each bit has a specific meaning, Okay, and there are some nice detailed diagrams available from Festo that shows what each of those bits do. All right, and then same thing on the control side of things. The first 4 of the control words are bitmapped integers as well, so that you can effectively, set the appropriate bits to make motion happen. But what we're trying to do with today's video and with these user-defined function blocks is to handle all of this status word and control word type interface through user-defined function blocks. So if you utilize those particular tools, should pretty much take care of this for you. But it's always good to get the information so you know in detail what these control words and status words, how those are made up, and what the individual bits do. That's, of course, good information. We're just trying to make it as easy as possible through these user-defined function blocks. Now let's take a look at the user-defined function blocks that we provided for integration with the Festo. And as you can see here, these are all inclusive. These are of the style that a lot of PLC manufacturers like, which are these all inclusive, lots of inputs, lots of outputs, do it all with one function block type approach. And that's what we've done here. Now, I didn't design this from scratch. I basically modeled it after an existing add-on instruction that I believe Festo created for use with Rockwell type PLCs. So this follows the same approach. And again, it's quite substantial. You've got 21 or 22 input variables, I believe, and 16 output variables. And the user-defined function block is designed to be always on. Another thing I'll talk about during the Cscape demo is that I've created a variable structure so that it's easy for you to name consistently and easy for you to create all the variables you'll need to feed into and feed out of this user-defined function block. So that's a structure, and I'll go through that in the Cscape demo. Now, let's take a look at the input side of things. On the input variables, the first input variable you'll need to assign is the actual 12-word input array that is coming from the drive as the status word. So the same ones that you assign in the Modbus TCP configuration. And then the rest of the input variables are really the variables that you'll need to manipulate elsewhere in your program to set up the motion that you want to execute. Whether that is a sequence of moves going back and forth to particular positions, whatever you need in your application, you're going to manipulate those variables that are fed into the UDFB so that the UDFB can generate what's required to make the drive do its thing. Now, on the output side of things, the first output variable you have to assign is the status array of 12 words that's being sent to the drive as control words. So the user-defined function block is going to take those input variables that you've assigned and that you've manipulated. It's going to take that data, see what you're intending with your motion, and then properly set the output words going to the drive, the control words going to the drive, so the drive will react the way you want it to. And then pretty much the rest of the output variables that are assigned are variables you can monitor, okay, that show you what's happening in the drive. All right, so the UDFB is generating a bunch of useful, mostly monitoring data that you can use to see that the drive is reacting the way you want. If there's any faults, you'll see that. If you've got a home reference, you'll see that, those sorts of things. You'll see the actual position, you'll see the actual velocity, those sorts of things. So other than that first output array, the rest of those output variables are ones you're going to want to monitor and use elsewhere in your logic for that purpose. Okay, now in addition to this all-inclusive user-defined function block for controlling motion, we've also got a very simple user-defined function block we've included that will allow you to very easily see that your Modbus TCP connection is healthy, because that's critical, obviously, because all the status words and control words are exchanged at high speed over Modbus TCP. So you're going to want to know you've got an okay connection, and if you have a faulted connection, you're going to want to feed that in as one of the inputs to the all-inclusive point-to-point user-defined function block that I just reviewed on the previous slide. So enough slides. Let's dive into the demonstrations today, going through what's happening in Cscape and then going through what's happening on the bench. All right, here is our demonstration program that includes the user-defined function blocks we've talked about. So let's kind of go through this now. This will take a little bit of time here. Okay, first thing is we need to make sure we import in the UDFBs that we need to use in our project. And of course, those are downloadable from the Horner website to the links that are tied to this video. So how do we do that? Well, under Logic Modules, we right-click and select Import Logic Module. And then that will pull up a dialog that'll allow you to navigate to the file location on your computer where those two UDFB files exist, so you can import them into your project. And when you do that, they show up down here under UDFB modules. Now we have two of them, okay? We have the main one that we've talked about that handles motion, okay? That's the really significant UDFB. And then we have this simple user-defined function block that gives us a nice convenient way to consistently and easily find the status of our Modbus communications with the drive so that we can feed that to our larger function block that is handling motion. Okay, so that's what we're looking at here. We've got to get those UDFBs into our project before we can start using them in our program. The other thing we have to do is we need to make sure that we've set up the Modbus TCP communications. But before I dive into that, let me go down here to the program variable area under global variables. Okay, so we're in the global variable section. And let me talk about a particular structure that I have created that would also help you in your application. So what is this structure? Well, it's a structure that I've named FESTO Drive PTP, or point to point is what that stands for. Okay, so if we scroll down here under where our structures are all listed, then you can see it's existing right here. Let me expand that. And this is really quite a significant structure. So what this structure is, it's really a structure of all the variables that you're going to need, that would include all the variables you're going to need for your Modbus TCP UDFB usage and for your FESTO Drive UDFB usage, and including some for your Modbus TCP configuration as well. Now, why would I go to the trouble of creating this structure, and why is it useful? Well, what it does is it makes all of the variables you're going to need in your program that you're going to have to create all part of the same structure. So you can, if you had multiple axes, let's say, axis X, Y, and Z, you could very quickly create all the variables you needed for your application by literally creating three variables, axis X, axis Y, and axis Z, if you chose to name them that, of the type of this structure. Okay, and this structure is called FESTO Drive PTP. So what I've done here in the global section, if we go up to the global section, okay, you can see that if I go up a little further, there we go. I've created a variable called axis X, all right, of the type FESTO Drive PTP. That's the structure name. And now all those subvariables are available and ready to go. And if I had multiple axes, I could create every variable that's needed for each additional axis by creating one more variable of this type. So that's just really handy, and it's excellent, an excellent way of doing it. And so taking advantage of that particular structure that I've created for you is probably a really good idea. Okay, one more thing I want to mention here. Now, generally with variable-based advanced ladder, you don't have to do a whole lot of mapping, really very little, frankly. In this case, what I've done for convenience sake is I went ahead for my axis X variables, and I went ahead and mapped those starting at register 1001. Why did I bother to map them at all? Well, when you're dealing with Modbus communications, Modbus is in words, okay? And there are times where if the words need to be combined, then you really need to have those mapped together, okay? So for instance, data is coming in as words or going out as words, but you need to interpret it maybe as a double integer, for instance. So in order to make that process easier, I went ahead and mapped all of my axis X variables starting at R1001. Again, because this is all in one big structure, all I had to do is just map one starting variable and that's it. Okay, and then the other thing I've done down here that I use elsewhere in my program is a couple cases where I have double integer value, which is integer values, which are actually combination of Modbus integer values coming in or going out. For using those variables in my program, I use them on a status and control screen. I've got that commented over here. So by also mapping these 4 variables, which were combinations, it just made it easier to make that happen. So that's really what that's all about. Again, if I would have tried to place a double integer data field on a screen that was really 2 single integer values concatenated together, I would get a type error. Okay, it wouldn't work. So by creating this new variable that's truly double integer, that's mapped to the same location where those 2 integers are located on the Modbus side of things, then boom, it works just fine. Okay, I just wanted to cover that with you briefly. But the keys here are, again, utilizing that structure so that all of the variables you're going to use in your program, for the most part, are all created with a single entry. All right, so the next thing I want to do is let's go through now the Modbus TCP configuration. Okay, so I'm going to go over here to the hardware configuration. Okay, and I'm dealing with a Canvas 7 here. So under LAN, all right, I've got to make sure that I have at least my IP address and net mask configured, and they could be tied to variables. I've just got them hard-coded here. And then, of course, down here on our Ethernet port is our Modbus client protocol that we need to select. And we have our 3 levels of configuration. All right, so under network, most of this is just defaults. Timeouts have been reduced here and here, okay? And I've added a Modbus TCP disable bit, and I've added a status register. Now these are, in my demo program here, other than a few other rare exceptions, these are one of the few variables that aren't included in that structure that I just talked about, because these really are tied to the Modbus master functionality or Modbus client functionality of the OCS. They're not tied to an individual axis. So if I had 3 axes that I was talking to with this system, 3 different drives I was talking to, I would still only need 1 of each of these variables. So that's why they're not part of the structure. Okay, so that's the configuration here. Under devices, in my example here, I've just got 1 device, okay, which I've given a convenient name. Okay, I could have called it whatever I wanted. The IP address is here. I need the 5-digit addressing. And then this is where I've started to use the variables that are part of the structure. So anytime you see a variable that starts with axis x dot, remember I named the variable axis x that was of that structure type. I'm going to see, these are all variables that are included in that structure. So when I go to select a variable, I can just make sure that, let me go ahead and back up a little bit here so you can see that here. All right, so axis X, if I expand axis X, that's where all these variables are located. All these, I call them subvariables, whether that's the proper term or not, I don't know, but that's where all these variables are located. So when we're adding these user-defined function blocks and doing this Modbus configuration, we've got our variable names all pre-created. In this case, I was just doing this variable right here, the server disable. Okay, so there we go. And again, I've also named the variable, so it's very easy to see where you want to put them in your program. Okay, and then in addition to this server disable bit, which hopefully you'll never need to use, there's also this server status bit, which is important to use, and you'll see why here in a minute. Okay, so that's our device level, and then on our scan list, we've just got 2 entries. We have 12 pulled read entries, or Modbus data, starting at 30,001, that's the read data. And again, axis X is our prefix. So here's our drive status is the variable that's part of that structure. Okay, that's the array, 12 words long. Okay, so that's the first entry. The other entry is starting at 40,001, that's our write data. And again, drive control is our array name here. Okay, so that's our Modbus TCP configuration. All right, so that's demonstrated. All right, now let's take a look at these user-defined function blocks that we've created. Okay, or that I've created that you can import into your project. Okay, so let's start with the first one. Now, first of all, if you're curious, how do you drop these into your program? Where are they in the project toolbox? Let's go ahead and close our variable window here so we have a little more space. And you'll notice at the bottom of the project toolbox when you're editing your logic, you've got this UDFBs category, and you'll find them here. Okay, so when you want to drop them in your program, you can just select them here, click, and away you go. Now, the first thing you'll be asked to do once you place them in your program is to name them, to give them an instance name. Okay, and I've called mine, in the case of this Modbus TCP, okay, drive status UDFB here, I've called mine Axis X MSTP. That's the name of the instance of my user-defined function block. And then if I double click here, you can see this is a really simple user-defined function block. All we have are 2 inputs and 2 outputs. Our inputs are that client status array that I just configured as part of my Modbus TCP configuration. Okay, so that was the status for the OCS Modbus, or the client Modbus. And then the other input is those 2 consecutive words. It's part of this array here. This was 4 consecutive double words. This is 2 consecutive single words. And then here's that same variable name that I created under the slave status, or the server status here. Again, all part of this one is part of my structure. And then the outputs, we just have 2 outputs, and they're both Boolean. Okay, we've got Modbus TCP OK and connection failed. Okay, so we'll know from the outputs of this function block if our Modbus is OK or if it has faulted. And this connection faulted bit is important because that one will be fed into the next user-defined function block, which is our main user-defined function block that I'm going to go through next. Okay, this main user-defined function block, this is that major one that I showed just a few minutes ago in the slides that has all those inputs, 22 inputs, I believe, and 16 outputs. So that's a lot of inputs and a lot of outputs. But, you know, this is one of those styles of function blocks that's kind of similar to, you know, I guess what customers are used to for those who've programmed Rockwell before. Rockwell has some of those add-on instructions that are available that are just ginormous. So this one really kind of mimics that style of user-defined function block, the all-inclusive user-defined function block. So that's why this is so large. Most of the UDFBs I create are smaller, you know, more simple function with just a couple inputs and a couple outputs, or maybe a few more than that. But this one is pretty much all-inclusive. And every single input variable and every single output variable that I've assigned to this user-defined function block in my program here are all starting with axis x dot. So that means all these variables are part of that structure. So I can very quickly, you know, either type them in or select them from the list, you know, by pressing this browse button here. And I can very quickly and easily get those variables assigned. You'll notice my structure names the variables very similarly, if not exactly, the way that the function block inputs are named and the way that the function block outputs are named. If we eventually get down here to where the outputs are, there we go, where the function block outputs are named. So again, it's a little bit laborious to get this thing set up the first time, but I've made it just as easy as possible. Again, you can tell what the name of this variable needs to be pretty much if you want to follow my naming convention by just axis x dot and then pretty much, for the most part, type in the name and you're good to go based on how the function block input or output has been named. Okay, so again, we've got all these inputs and outputs, all with their specific function. And one of the great things I will say, again, I modeled this user-defined function block after an existing function block that was created by the folks at Festo. I'm sure that it was created for, it's similar to an add-on instruction they've done for Rockwell. I've tried to mimic that functionality as much as possible so that any customers who may be using both Horner and Rockwell would have a really easy time using this particular function block. And I thought since it was nicely designed by the Festo team, I would mimic it here. So many thanks to those guys for mimicking that. Now you'll notice with both of these user-defined function blocks here, they're designed pretty much to be always on, okay? So always receiving power, okay? So no reason to have anything other than just always on here for their proper operation. Okay, so those are the 2 user-defined function blocks. A couple of the things I'll show you in my demo program before I get to the screens. Now, again, kind of mimicking what some customers do in other PLCs with other PLC brands, is I've just for convenience purposes in your program, I've also got this on a screen, created for a screen. I've got this, a series of bits that you might want to monitor, just available here with a couple of consecutive rungs with dummy coils at the end. So you can very quickly and easily see the status of these bits if that's important to you. So just let me kind of demonstrate that by putting this into debug mode. So when we're into debug mode here, you'll notice that as soon as we get all the data read, there's a lot of data to be read here, not just on these rungs, but on all of the other rungs. Okay. You'll notice I can very quickly and easily see which bits are on and which bits are off just by looking at these particular rungs here. So this is the EPOS control functions. Okay, so that's one of the inputs are the EPOS control functions, inputs to the user-defined function block. And then here are more status that we can look at here. Okay, this is feedback. Okay, from the, or is this feedback? Let me take a look here. So more status bits here, as you can see. And then down here in my program, all we have is just a single rung that sets velocities and overrides to default values on power up. So that just sets things off to a convenient known position or known state, if you will, on power up. Okay, so that's really all we've got going here in this ladder logic. Just these two function blocks, user-defined function blocks, and then a couple other rungs for convenience purposes for monitoring status, as well as just a single rung for setting things up for some default values at power up. Okay, now let's take a look at the screens I've created. Now I'm just going to cover these very, very quickly because you're going to see these in more detail on the bench. Okay, so let me go to user interface and main screen here. And I'll highlight a lot of these on the bench, but one of the things I want to show you is we do have a single screen that you can use to monitor all the words of status inputs and monitor all the words of control outputs. And then for some of these, the ones that have this little extra button here, these are really jump buttons, you'll also be able to see the detail within an individual status word or control word. So if I go here to the ZSW screen, which is accessed by pressing this jump button, you'll be able to see, you know, the individual status of each of those bits, because ZSW1 is one of those bitmapped status words where each bit has its own meaning. And you've got 4 of those on the input side and a few of those on the output side as well, where you can see the detail. All right, now the rest of the screens I'll just review with you as we take a look at things on the bench. Okay, let's take a look at the system on the bench. Now I've designed the screens on this demo program to kind of walk you through the process of making sure, you know, everything's set up properly so that you can begin instigating motion. So you can see the different steps you'll need to take in your logic program to kind of automate that process, if you will. Okay, so let's get started on the configuration screen. All right, so a couple things. First of all, really the goal here on the screens, visually at least, is to kind of get everything green. All right, when everything's green, we should be able to instigate motion. All right, so we've just powered up the drive a minute or two ago. All right, and we do have Modbus OK green, and we are counting up messages. Everything else, though, looking pretty red. Okay, we do have a valid velocity. Okay, that's important. And then down here, these are all bits that need to be on if we're going to instigate motion. Okay, and as you can see, I turned those on. Now my lockout went green. All right, so that's looking good. However, my axis reference, all right, is still not on. Okay, so that means we just don't know where home is. The system just doesn't know where home is. So we need to get that established before we can really move. All right, so over here again, we're still initializing because we haven't enabled our axis yet. Let's go ahead and do that now. Okay, now we're solid and we're servoing. Okay, we are in home mode. Okay, so you'll have to set your modes the mode pos variable to its proper number, depending on the mode you're looking for, whether it's, find home in the current position, which is what we're looking for here, relative move, absolute move, etc. But when I'm in mode 5 and I hit the execute mode button, then the system should basically establish wherever I am right now as its reference. So let me do that now. Okay, and my axis reference went solid green. Okay, looking good. All right, now the only light that's not solid green right now is my direct mode light. So let me go ahead and change my mode over to absolute positioning mode, which is what I'm using for this demo. Okay, and as soon as I did that, then okay, now we're in direct mode and we're ready to go. All right. Okay, so we're all green on this screen. Let's move to the move precondition screen. Here we are. We're all green here as well. If we had any kind of axis error, we could easily clear it or attempt to clear it here with this ACK error bit. Okay, that's just the equivalent of the clear error bit. All right, so we're all green here. Let's go to the execute move screen. All right, and we're looking good here as well, okay? Okay, so this is where we can actually instigate moves. All right, so our acceleration, deceleration, and the overrides for acceleration, deceleration, and velocity are all set at reasonable levels. And really, those have to be set at reasonable levels before you can even find home the first time, but hopefully they'll be set appropriately in your program. Okay, our actual position, which is the feedback we're getting here, is 0. And if we want to move that position, since we're in absolute position mode, I should be able to establish a new position here. Okay, let's go with 25. All right, and then while I'm in absolute position mode, if I hit the execute mode button, I should see the system move. And it did. All right, and there we are to our new position, which is what we're looking for. And so in this state, of course, we can just move back and forth to wherever we need to be, depending on what the application is doing. Okay, so let me change the position again here. Let's go to 40 this time. There we go. All right, and away we go. So we've established the steps that are needed in order to get motion instigated and active. And then one other screen I'll show you here, and that is kind of a status and control data screen that just is showing the current values for the status input words and the control output words. Now there's 12 of each. Of course, the 12th one is reserved, so in reality it's 11 of each. But you can see here for each of the status inputs and control outputs, we have status that we can look at here for our system. Okay, so hopefully this demonstration program in combination with the user-defined function blocks that I've created will really make it easy for you to create some good motion control programs using the FESTO system. Okay, that does it for our material for today. This is where I remind you we're here every Tuesday at 2 o'clock. We always have somebody standing by to answer your questions if you're watching live. If you're watching on replay, give us those questions and comments in the comment section, and we'll get back to you as soon as we can. I love seeing those comments. It gives me something to look at first thing in the morning to start my work day. Okay, we've got our 2025 Horner training schedule established. Don't forget to sign up for training so you can get the information you need and make sure that your slot is reserved. Okay, lots of trade shows coming up in 2025. We wanted to have this posted here on the screen. Feel free to freeze frame it so you can see where we're going to be in 2025. Okay, lots of ways to interact with Horner online. You can do so on our website. You can do so on our YouTube channel, where we have hundreds of videos like this one. We're also very active on LinkedIn. Okay, next week, New Year's Eve, we've got a IEC-based topic using the case instruction in IEC structured text. It's an instruction we've really never covered much on the channel here. I think we covered it very, very briefly when we had our friend John Seymour in to talk about IEC, but we're going to give it a little bit more detail so you can use the case instruction in your next IEC project. Okay, if you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, which I guess is New Year's Eve, let's all get out there, enjoy time with our families during this holiday season, and do plenty of good.